Welcome back. In the last video for this section, we're going to look at definite integrals and substitution. So for here, there's a little bit of a twist, and we have two different approaches that we can take, and both are fine, so it's really up to you which you choose. When we're thinking about looking at a definite integral, remember that we have our variable that we're integrating with, and then we have the values for that variable. That means that if we're switching to a different variable, we have to think about what's going to happen for those limits of integration. So one approach is to do the following. We have our definite integral in terms of x, and then we change it into a definite integral in terms of u. And then that means that we're also adjusting our limits of integration so that they're also in terms of u as well. So we start off with a definite integral with x's and x values, and we turn it into a definite integral with u's and u values. And then that's sort of nice because then once you find your antiderivative in terms of u, you don't need to go back in terms of x because you have u values. You can go right ahead and use those u values and put them on in. The other approach is to ignore the definite integral side of things for now and just treat it as an indefinite integral. And so there you can do your substitution and you can find an indefinite integral in terms of u instead. Once you do that, that'll allow you to find yourself an antiderivative. And once you know an antiderivative in terms of u, you can use that substitution to rephrase that as an antiderivative in terms of x. And then now that you've got that, you can go back to your original definite integral. Now that you know an antiderivative, you can just evaluate that antiderivative in terms of those x values. So for this one, I'm going to actually take the second approach for this one. I'm going to ignore the limits of integration for now and just first figure out what can I find as an antiderivative for x squared plus 4 to the third times x dx. And so for this one, a substitution seems to be a good choice. Of letting x squared plus 4 be u, and if that were the case, then du would be 2x dx. Of course, I don't have 2x dx here, I've just got x dx, and that's easy enough to fix. That would be then half du is x dx. So I can go and do my substitution, and I can say that for an indefinite integral of x squared plus 4 to the third would become x squared plus 4 to the third becomes u to the third, and x dx becomes half du. And then this is easy enough for us to find our indefinite integral for. So adding 1 to the power, dividing by the power, and I get 3/8 u to the 4/3, or 3/8 x squared plus 4 to the 4/3, and that's, of course, plus constant c. So right now what we've done is we've found the antiderivative, or an antiderivative, for the indefinite integral. It's 3/8 x squared plus 4 to the 4/3 plus constant c. Of course, you can ignore the plus constant c because what we're going to do now is look at the definite integral side of things. So now that we know that integral from the integral of x times x squared plus 4 to the third, now that we have an antiderivative for it, then for the definite integral, we just have to evaluate that antiderivative between 2 and 11. So we just have to take that 3/8 x squared plus 4 to the 4/3 that we just found as our antiderivative and evaluate that between x being 2 and x being 11. So let's do that. Putting in the 11 and then putting in the 2. And then just a little bit of cleaning up after that. So for this first one, 11 squared plus 4 is 125. 125 to the 4/3 is 625. 2 squared plus 4 is 8, and 8 to the 4/3 is 16. And there we go. We've got what turns out to be 1,827 eighths. So our plan for this problem was I did approach number 2. I ignored the limits of integration. I treated it as an indefinite integral first to find myself an antiderivative in terms of x. And then for the definite integral, I just evaluated that antiderivative. Now, the other approach was the first approach, which I think is a little bit more streamlined. It's a little bit more work up front, but it's a little faster later on. So for this one, we're going to turn it from a definite integral in terms of x into a definite integral in terms of u. And so that means when we do our substitution, we're also going to be substituting our limits of integration. So let's get ourselves going here, thinking about what we're going to choose as our u. So I'm going to start off with on the side saying to myself, well, I've got cos cubed times sine. If I had u being cosine of x, then du would be negative sine x dx. And of course, I could also say then that negative du is sine x dx. So as far as the substitution goes, I have part of my work done. I can say, well, I know that it's going to be an integral of, instead of cosine cubed, it'll be u cubed, and instead of sine x dx, it's negative du. But I have to change my limits of integration, because if I were to put 0 and 3 pi over 4 here, then this would be wrong. This would not be true. The 3 pi over 4, that's a value for x, and the 0, that's also a value for x. I'm integrating with respect to u, which means for a definite integral, the limits of integration need to be values of u. So this is what we need to figure out is, as x goes from 0 to 3 pi over 4, what happens for the values of u? So for our lower limit of integration, we said that x was 0, and for our upper limit of integration, x was 3 pi over 4. So the question is, what is the lower limit for u then? And what's the upper limit for u then? So when x is 0, u is cosine of x, so in other words, u is cosine of 0, which is 1. So our lower limit of integration is 1. Our upper limit for x was 3 pi over 4. U is cosine of 3 pi over 4 then, which turns out to be negative root 2 over 2. So our upper limit of integration is negative root 2 over 2. So you'll notice here that my limits of integration seem to be in the wrong order, going from a positive number to a negative number. And that's, again, following the order that the x values did. X goes from 0 to 3 pi over 4. When x is 0, u is 1. So that's why 1 was my lower limit of integration. And for the upper limit for x, we got negative root 2 over 2 for u. So my upper limit is negative root 2 over 2. If I want to switch things and have it switched from top to bottom, of course, that just changes the sign of my integrand. So right now, my integrand was negative u cubed, so I can change it to a positive u cubed and switch my limits of integration. Okay, so now we're pretty much ready to go, because the only thing that I have to do now is just integrate and evaluate. And so when I do that, I have u cubed du, which is u to the 4 over 4, or 1/4 u to the 4. And I'm going to evaluate that between my u values, between my u value of 1 and negative root 2 over 2. So now we'll just evaluate these. I don't need to go back in terms of x, because again, these values here are u values, so I can go right ahead and put them into what u is. I can say, well, we evaluate at 1, so that would be 1 to the power of 4, and then minus, and we'll evaluate at negative root 2 over 2. So 1 to the power of 4, of course, that's just 1. And negative root 2 over 2 to the power of 4 turns out to be a quarter. So we have minus quarter times a quarter, or minus 1/16. And that gives me 3/16 as my final result. Of course, if you don't feel comfortable doing that, you could always go right ahead and do what we did before and ignore the definite integral side of things, keep it as an indefinite integral, find an antiderivative in terms of x, then you can go ahead and use your x values. But for myself, personally, I feel like since you're going through the effort of substituting for x, then you might as well take the extra step and change your limits of integration, and then that saves you a step. So that once we've integrated in terms of u, we just stay in terms of u and evaluate with our u values, and then get ourselves a number that we get as our answer. Okay, so one more to look at here. I want to find the area bounded by the graph of this function, the x-axis, and those lines. I don't know what the graph of this looks like off the top of my head, and I also don't really need to care that much because I know that the denominator, no matter what, since the denominator is a perfect square, the denominator is going to always be something that's positive. X squared plus 1, the smallest it'll ever be is 1, and then squared is 1, so the smallest the denominator will ever be is 1, and it will just be numbers that are 1 and larger. So my bottom is always going to be positive. And for the numerator, you can also say, well, if x is positive, then the numerator is positive. So at least for positive values of x, and those are the ones that we're interested in. We're interested in values of x between 1 and 4. This graph should be above the x-axis. So I don't need to worry about what it looks like. I know that at between 1 and 4, the numerator and the denominator over that whole region will always be positive. So that means that this function is above the x-axis. So whatever the area is could be expressed as a definite integral from 1 to 4 of that x over x squared plus 1 squared dx. Okay, so now I guess let's start thinking about doing a substitution to help ourselves out here. I'm looking at this x squared plus 1, and I can see for sure that that seems to be a good thing to let u be. And that's because that means that du would be 2x dx, which is almost what we have. We've got x dx, so in other words, I could say half du is x dx. And I'm going to take that second approach. I'm going to just turn things into u and keep things in terms of u. Why not? So I would say then for my integral, I will be integrating x dx, that's half du. And instead of x squared plus 1 squared, I'll have u squared. I'll have to figure out my limits of integration though. So I know that my lower limit and upper limit for x were 1 and 4. So the question is, what do I get for u? So when x is 1, the value for u is 1 squared plus 1, which is 2. So my lower limit should be 2. And then for x, the upper limit was 4. 4 squared plus 1 is 17, so the upper limit for u should be 17. And then now I don't need to do anything where I go back to x's afterwards. I can go right ahead and just integrate this. So I'll integrate from 2 to 17 u to the negative 2 du. And once I find myself my antiderivative, which not hard to find, we'll just add 1 to the power, divide by the power, and now evaluate that between my limits of integration between 2 and 17. I'm just going to clean this up a little bit. This is negative 1 over 2u going between 2 and 17. So we'd have negative 1 over 2 times 17, which is 34, minus negative 1 over 2 times 2, which is 4. So we have a quarter minus 1/34, which is 15/68. And there we go. That's the area under my curve. All right, we have a position function, and it gives us the position of an object at a time, t, and we wanted to know average position over an interval. So if I'm looking for the average position, I know that the total position would be the definite integral. The average position we'd find by dividing by that distance between the beginning and the end. So 1 over pi minus 0. Okay, so I can make this look a little bit nicer. This, of course, is just 1 over pi. Integral of 0 to pi sine t cos t plus 3, cos t plus 2 rather, cubed dt. So for substitutions, I'm going to think about maybe having u be the denominator of the cos t plus 2. And the reason I'm thinking that's a good choice is because the derivative of cosine is negative sine. So du is negative sine t dt, or in other words, negative du is sine t dt. So that's kind of fixing some of our work here. I can say then we're going to have 1 over pi, and then we'll have a definite integral of, and we'll need to figure out what that is. In the denominator, I'll have cosine of t plus 2 cubed is the same thing as u cubed. Sine t dt, that's negative du. And now for my limits of integration, we had t was going from 0 to pi. So in other words, t was going from 0 to t being at pi. When t is at 0, u would be cosine of 0 plus 2. That would be 1 plus 2, which is 3. So 3 should be my lower limit of integration. And when t is pi, u is cosine of pi plus 2. Cosine of pi is negative 1, so we'd have negative 1 plus 2, which is 1. So my upper limit of integration is 1. So again, we're kind of in the same boat that we were with the last problem, where we have our limits of integration seem to be in the wrong order. We have the bigger number on the bottom and the smaller number on the top. But I can do the same workaround where if I switch my limits of integration, then that'll change the sign of my integrand. So instead of being negative 1 over u cubed, it would be positive 1 over u cubed. So that's what we'll do here. We'll say I'll change it, my limits of integration, to now be, instead of going from 3 to 1, we'll have it going from 1 to 3. And now it'll be positive 1 over u cubed, or u to the negative 3. Okay, so now I'm just going to evaluate this. I'm going to find my antiderivative. For u to the negative 3, it's u to the minus 2 over minus 2. And we're going to evaluate that between 1 and 3. Just to make this a little bit nicer, this is negative 1 over 2 pi u squared, going from 1 to 3. And again, these are u values, the 1 and the 3. So we don't need to go back and turn things into x's. We can just go right ahead and put in what we have in terms of u. And specifically, we have that u is 3 and 1. Those are our two values. So we get negative 1 over 2 pi times 3 squared, and then minus negative 1 over 2 pi times 1 squared. So we'll have 1 over 2 pi minus 1 over 18 pi, and that gives me 4 over 9 pi once I simplify it. And so there we go. That is the average position for my object over that interval from 0 to pi. Okay, one little last one to look at, and this one is, of course, it's a definite integral problem, but this is a little bit of a proof problem. We want to show that these two things, the definite integral from 0 to pi over 2 for sine n of x, and cosine n of x over the same interval, that they have the same definite integral, no matter what power of n that we're looking for, as long as n is something positive. So I guess the first thing that I'm going to do here is take a little bit of a note of this hint. And this is the complementary angle theorem for trig functions, telling you that sine of 90 minus x and cosine of x are the same thing. So this is sort of my plan here on how I'm going to show these two things are equal. So number one, to show that they're equal, the variable that we're using doesn't really matter here. So if it's cosine of x dx, that's the same as if I'd had it cosine of u du, or whatever other letter I feel like choosing. Because again, this is a definite integral. So since this is a definite integral, it doesn't really matter whether we're using u's or x's. I can use whatever variable I feel like. So actually, this is my plan here. I'm going to do a clever little substitution of what if I were to replace the x with pi over 2 minus u. So I'm going to start off with the left side of my equation. I'm going to start with that definite integral, and I'm going to do that substitution. So when I do that, let me just get myself going here. Start with my definite integral of 0 to pi over 2 of sine n of x dx. And we said for our substitution, we're going to choose to let x be replaced with pi over 2 minus u. So why are we doing that? Well, I mean, it's going to do one nice thing. Dx would be the same thing as then negative u du, or negative du rather. So I know what I can transform the dx into. That'll be negative du. So I've got part of my substitution already done. I can say, well, now it's going to be an integral of sine to the n of pi over 2 minus u. It'll be, instead of dx, it'll be minus du. And now we need to figure out our limits of integration. So for our limits of integration, x was going between 0 and pi over 2. So we need to know what's happening for u. So if x is 0, if I use the original substitution and have x being 0, then I'd find in that case u would be pi over 2. So my lower limit of integration for u should be pi over 2. For the upper limit of integration, if x is pi over 2, if pi over 2 equals pi over 2 minus u, then u would have to be 0. So the upper limit of integration in terms of u would have to be 0. Okay, so now we're part of the way there. I'm going to, again, this is the same sort of thing we've seen a few times now. Our limit of integration seems to be in the wrong order. So I'm going to swap it from pi over 2 to 0 and turn it to 0 to pi over 2. And that's going to change the sign of what's inside from a negative to a positive. And there we go. I can now use my little identity that I have there. I know that sine of pi over 2 minus x is cos of x. So sine of pi over 2 minus u is cos of u. Or sine to the n of pi over 2 minus u is cos of n to the u. And now here I'll just finish things off, and now we'll finish things off with one last little step, which is to remind ourselves that since this is a definite integral, whether I'm integrating u with respect to u or x with respect to x doesn't really matter. So actually, this definite integral from 0 to pi over 2 of cosine of n, power of n of u du, that is the same thing as from 0 to pi over 2 cosine power of n of x dx. So actually, we can now make our big conclusion that, yes, the definite integral that we get from 0 to pi over 2 of sine of power of n is the same as the definite integral from 0 to pi over 2 of cosine to the power of n.